This is problem 3.18 from Horton's 5th edition. The question reads, calculate the approximate concentration of the uncharged form of alanine C below. So normally if I were to draw alanine, I would draw it in this zwitterionic form as such, in which the amino group is positively charged and the carboxyl group is negatively charged. The book is asking us about the concentration of an uncharged form, and they show that drawn as such, in which the amino group is unprotonated and the carboxylic acid portion is unionized. So I would call this the zwitter for us and the non-ion here. And it asks what's the concentration of this non-ionic form at 0.1 molar concentration, so 10 millimolar. We have to factor that in at some point. At pH 2.4, which is the pKa of alanine. You can refer to table 3.2. pH 6.15, which is the isoelectric point, and I'll show you that. pH 9.9, which is the pKa of the ammonium group. So let's look at this. Normally we would consider the ionization by drawing the other forms. At a low pH, we expect that the carboxylic acid, the carboxylate, will be protonated, and we will have a cationic form. And at a higher pH, the amino group will be deprotonated, and we will have then an anionic form. This is pKa1, and it's 2.4, and this is pKa2, and it is 9.9. The pi here, which is 6.15, can be calculated when there are two groups, let's say a base and an acid, to consider. It's quite complicated if there are more than just a base and an acid, and in this case it's simply the average, so it's pKa1 plus pKa2 divided by 2, and that's 6.15. So that's the intermediate between the two pKa's, where we expect the zwitterionic form to be most common. So the book makes an assumption, and that assumption is probably reasonably close to reality, but the reality is something that we don't really know what the answer is, so that's why we're making an assumption. So what the book is assuming is that if we consider this non-ionic form, we can imagine that the relationship between these two is the acidity of the amino group, and that's also going to be 9.9, so I'm going to say that's pKa3, and we can imagine this equilibrium here, which I'm going to call pK4, and that's the deprotonation, the carboxyl group, so we can imagine that pK is 2.4. So essentially what the book is saying is, let's assume that pK3 is the same as pK2, and pK1 is the same as pK4 is the same as pK1, and that's an assumption because the acidity of this carboxyl group here is going to some extent reflect that it's attached to a cation, and in this case the non-ionic form pK is likely to be different because there's not a cation attached to it, but it's very hard to figure out what that would be experimentally or even theoretically. So I'm going to draw this here as a simplifying assumption. Let's imagine that we have, in this case, I'm doing this wrong. Let's imagine RCOOH is in equilibrium with RCOO minus, right? That's governed by 2.4. And in this case, we have our NH3 cation in equilibrium governed by a pK of R NH, sorry, that's not very legible, NH2. So we have two acidities. This one here, what's happening here, is governed by pK 2.4, and what happens here is 9.9, right? The acid has a low pK, the base, or conjugate acid of the base, has a high pKa. And so I'm going to show you graphically before calculation what this means, and let me try to draw this relatively carefully. So let's first imagine a plot where we're looking at pH 7, 6, 5, 4, 3, 2, 1. We can keep going, but this is all we need to show. 8, 9, 10, 11, 12. That's enough. So, and on this axis, we can imagine the percent of a certain form. So let's understand first this carboxylate group. So if I use for the carboxyl, the protonated, the carboxylic acid form, this at pH, whatever this is, 0, we expect to be 100% in this form. And at its pKa, which is 2.4 here, so this is 3, 2.4 here, we expect it to be what? 50%, because pKa 2.4 means at this pH it'll be 50% unionized and 50% ionized. And at 1 pH unit below its pKa, it'll be 90% in this form and 10% in this form. So that would be 1.4, somewhere around here. And at 2 pH units below its pKa, that would be 0.4. It would be 99%. So we can do a point here. Likewise, at a pH 1 unit above its pKa, it will be only 10%. So that would be 3.4. 10% of that form, and at 4.4, 1%. So if I draw this, I'm going to draw it like this. It's not the best curve, and we can imagine extending this out, very, very low values. And if I want to show, bear with me while I change the pen color. If I will compare that to, let's use purple, to the deprotonated, the carboxylate form, then it's also going to be 50% at the pKa, and at 1 unit above the pKa, it's going to be 90%, and at 2 pH units above, it's going to be 99%. At 1 pH unit below, it's going to be 10%, and at 2 below, it's going to be 1%. And so its concentration as a proportion of total carboxylic and carboxylate is going to go up like this. So as the pH changes, the proportion of carboxylic acid versus carboxylate is going to change like this. Likewise, I can do that again. I'm going to change ink color again to something, let's say, a little bit green. And let's do the same thing now with the other group. So at low pH, it's going to be protonated, so let's consider RNH3+, and it's governed by 9.9. So at 9.9, which is all the way over here, we expect it to be 50%. 1 pH unit below that, we expect it to be 90%. Somewhere here, another pH unit below that, we expect it to be 99%. A pH unit above the pKa, we expect it to be about 10%. 2, we expect it about 1%. So we expect its concentration, relative abundance of all amino ammonium and amine to be this. And we also have, bear with me, I will try this color. We also have the base form here, completely deproteinized and neutral. And at the pKa, pH equal to the pK, it's going to be this. 1 pH unit above, it's going to be 90%. 2 pH units above, it's going to be 99%. 1 pH unit below, it's going to be 10%. 2 below, it's going to be 1%. And so we expect to have its concentration change as a function of pH like such. And what we're interested then is in what these other forms represent. So at very low pHs, I'm going to go back to, let me go to a neutral color now, such as black. So what we expect here, this is pK1 of interest, the PI is of interest about there, and pK2 of interest there. These are the three pHs we're interested in, 2.4, 6.15, and 9.9. And the question is, what's the concentration of these different species? So much below this, it's all the cationic form. As the pH increases, we get the carboxylic group ionizing to be a carboxylate. And until the amino group starts to deprotonate, till the ammonium group starts to deprotonate, we're going to have all zwitterionic here. So this regime is going to be dominated by the zwitterionic. Here we're going to have the cationic form, and here we're going to have the anionic form dominate. And the question is, what about the neutral? And the neutral form, this non-ionized form, is going to be the product of the concentration of this unionized carboxylic acid down here times the concentration of the non-ionized, the neutral ammonium. So where this curve, the product of the proportion of this times the product of the proportion of this, is going to be the concentration of the non-ionic form. And you see that where the carboxylic acid is not ionized, here, 100%, the amine is very, 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 very low. Very, very, very many pH units below, and very, very small. Likewise, where the amine is in its neutral form, the neutral acid form is going to also be very, very low. And even between there, where they're both low but not extremely low, it's going to be, the neutral form is going to be the product of these two concentrations. So it's going to be so low as to be insignificant. In the next part, I'll do it mathematically.